Hello everyone! Today we are going to talk about permutations, combinations and different points of view on both. These are based on the fundamental multiplication principle that we saw last lecture. Let's start with a simple example. Imagine the following game. You have an urn and you have 5 numbered balls in it. And you are going to draw one at a time. You look at it, take note of the number, and you don't put it back. So, you have the following recipe. You have the urn U with balls numbered from 1 to 3, 4 and 5. They are indistinguishable. And you are going to follow these steps. First step, you draw one ball. Take note of the number, don't replace it. Again, step number 2 is the same thing. 3, 4 and 5. You repeat this thing 5 times. In the beginning, you have 5 balls available. Then you only have 4, and then 3, 2, and finally it's just 1 left. As a result, you have the following outcome. It could be, for example, step number 1, you draw 5. Step number 2, you draw 3. Step number 3, you draw 2. Step number 4, you could be 1, and finally 4 at the last step. Okay? You have here a sequence of 5 numbers. In general, we can write this as x1, the outcome of the first step, x2 for the second, and so on, is a string, is a sequence of numbers. And so, we call it a 5 tuple. The order matters, the order of your results matter. Okay? The set of all these outcomes, let's call it omega. So the procedure, let's call it C. We are going to see Y in a minute. 5p, and the omega, which are the set of outcomes of C 5p, is omega 5p, which is all the 5 tuples, x1 up to x5, where x1 must be different from x2, which must be different, etc., up to x5. The numbers are different because we are assuming at each step that there is no replacement. Okay? Now, what's the size of this set? How many elements does it have? How many 5 tuples does it have? Well, if you remember the multiplication principle, you know the following. If you have a choice that can be realized in n1 ways, and you have a second choice that can be realized in n2 ways, and so on, then the number of ways in which you can realize this sequence of choices is n1 times n2, and so on. And so, you can you have to adapt this way of counting to this procedure C5p. But you see, you don't have a sequence of choices. You are just drawing the balls. So, it is useful to rephrase this thing as a sequence of choices. Let's do it. Instead of drawing a ball, you can say, well, you choose from 1 to 5. Then, second step, you choose from 1 to 5, except the result that you get from the previous step. Step number 3, you choose again from 1 to 5, except the result from 1 and 2, and so on. Okay? If you follow this recipe, you get the same outcomes. Not this one, but this one. Okay? The general one. You get also a string of numbers, they cannot be repeated, and the omega is the same. So this procedure of choosing, of this sequence of choices, is equivalent to drawing the balls from the urn. Okay? Now, but for this sequence of choices, you can actually use the multiplication principle. So, you have, for the first step, which the first step can be realized in practice in n1 ways, which is 5, because there is 5 numbers to choose from. step number 2 can be realized in n2 ways, or 4, because you can no longer choose the previous number, and then n3 is 3, and 4 is 2, and then 5 is just 1 possibility left. By the multiplication principle, we know that the size of C5p, that is, how many choices, how many realizations can you have for this sequence, the size of C5p must be the product of these numbers. So it's 5 times 4 times 3 times 2 times 1. Okay? This string of numbers appears many times, and so we use an abbreviation for it. We write it like this. You write 5 because it starts at 5, and then exclamation mark. You read this 5 factorial. 5 factorial is by definition this thing that you have here. For example, 3 factorial is 3 times 2 times 1. 0 factorial is by definition 1. And 5 factorial is 5 times 4 times 3 factorial, because 3 factorial is 3 times 2 times 1. Okay? Can you see? Now, it's a good definition because it saves space. You have to write this, now you just have to write this. Okay? Okay, now that you have the size, or many ways you can realize this in practice, well, what does this have to do with the size of omega? Let's make a diagram to see. Because remember, our goal is to know the size of omega 5p. For the first choice, let's make a tree diagram. You have 5 possibilities. So you could be choose 1 or 2 or 3 or 4 or 5. The second choice, if you on the first choice you chose 2, then you only have 4 possibilities. If you have chosen 4, you only have 4 possibilities, and so on. But the 4 possibilities are distinct, because if you choose 1 on the next one, you can only choose 1, not 2, but 3, 4, and 5. If on the first one you choose 4, then on the second step you can choose 1, 2, 3, 4, no, but 5, because 4 was already chosen. Okay? Let's move on. On the step number 3, if you choose 3, you only have 3 possibilities now. It cannot be 2 or 3, so you have to be 1, 4, or 5. So these are the possibilities for this circumstance. Then 4, you only have 2. Two possibilities. It could be 1, not 3, not 2, not 3, but 4. And finally, the last step, only 1 choice possible. So let's make it's hardly a choice, because if you only have 1 option, but we still consider a choice. So it cannot be 2, 3, 5, or 1. So it must be what? It must be 4, right? And again here, it cannot be 2, 3, 5, or 4, so it must be 1. Your final choice. Okay? Now, let me just push this a little bit back. So it could be 4 or 1. Okay? Now, this tree represents all the possible realizations of C. Okay? And for each possible branch, each branch is a particular realization of C. And each particular realization of C leads to an outcome. For example, let's put it in red, outcome. So for this branch, it starts at 2, then 3, then 5, then 1, and then 4. Okay, can you see? Or it could be 2, it could be 3, 5, 4, and 1. And so on. So this is the set, all the possible, if you keep on going, all the possible outcomes. Okay? This thing in red is in fact omega 5p. All the possible outcomes. Okay? Now, for each branch has a one-to-one correspondence with the outcome. So that means that there are as many branches here, or many realizations, as there are outcomes. Okay? And so the size of C5p must be the size of omega. You see? So the size of omega 5p is the same as this. So you can look at it from this point of view. This is like a tree, the branches of a tree. This is the root. This is the tree. And each branch has at this end a fruit, the outcome. Okay? And of course, because each branch has a fruit, it means there are as many fruits as there are branches. Like this. Okay? Now, let's move on to something more important. And move on. Let me just look at it. Okay, let's look at it from a different point of view now. Let's look at it from a different point of view. Okay? Because you see, here, okay, why do we need a different point of view on this kind of experiments? Because in practice, in practice, different point of views might be useful. Okay, because you are doing the same calculation, but you arrive at the same calculation from a different way. Okay, you already seen this way of choosing. You already seen the drawing way from drawing the balls from the urn. But now let's see another way that leads to the same results. Let me write it downstairs. Here. Here. So let's again have a C 5p. You see the difference is here we are associating to each spot, you see, to each spot, each site a number. You see, we are associating to each site a number. But here we are doing in reverse. You are associating sites to the numbers. Okay. Let me just write. So the first step is to choose site 1 prime up to 5 prime to number 1. Second step is to choose a site 1 prime to 5 prime to the number 2, except the choice that you made previously. Okay, and so on. You just keep on going. 4, 5. Okay, the same thing. Of course, you cannot choose the same site. Let's make here the 5 sites. This is 1 prime, 2 prime, 3 prime. The sites are labeled by these indices, and you have here the numbers 1, 2, 3, 4, and 5. This is, by the way, the set U. Okay? Now, let's follow this recipe. What does it say? Choose a site from 1 to 5 to 1. Okay. So let's choose for the number 1, the first one. What site do we want to choose? Let's make it like this. For the number 2, it could be like this. For the number 3, it could be like this. Number 4. And finally number 5. You see? Following this recipe, you get again a sequence of numbers. So you get again a 5 tuple, just like we have here. In fact, just look at it. The same sequence of numbers that you have here is the same that you have here. You see? So we are producing the same results, the same outcomes from this or from this. So they are equivalent. They are distinct ways of thinking, but the outcomes are the same. Okay? This procedure generates what we call a permutation. This number, this sequence of numbers, is what we call a permutation. Okay? Because it's original order, and then you just exchange. You exchange the numbers, and you get a new sequence. So each number here is what we call a permutation. In fact, because these two things are equivalent, we can also think about the outcomes of this situation as permutations. Okay? Permutations of this thing. Okay? So, again, permutations are the elements of omega 5p. That's their name. Okay? Now, let's move on to something very important as well. Okay? Let me just write the final conclusion. The final conclusion. I'm going to write it here on the top because it's very important. The first conclusion for what we have been talking about. The first conclusion is this: if we have a set U which has n elements, okay, then the number n factorial, which is in this case is 5 factorial, see, 5 factorial, remember, is the size of the thing, remember, or again, the number of realizations of this procedure, because they are both equivalent. So if you have a set, then the number n factorial tells you how many sequences, how many permutations can you generate from the set U. This is very important. N factorial is the number of permutations, okay, that you get. That is the size of omega 5p, or how many ways you can realize this experiment or this experiment. So this is the first big result that we have today. Okay? What the meaning of n factorial. Okay? Now, let's make this more general. Because you see, here we are talking about from a set from 1 to you see, let me say like this. Here currently we have a set from 1 to 5, okay, and you are making as many choices as there are elements in the set. So to make this more general, instead of making 5, let's make fewer. Okay, let's cut this part and call this C, not 5 but now 4. I'm sorry, but 3, because there are only three choices. Okay, so you keep the same urn, the same size, or the same set with 5 distinct elements. You have the choices. Okay, let's erase this. What is the consequence? What is the consequence of reducing these? Well, the first choice you still can choose from 1 to 5, so you keep this part. On that second choice, you have here 4, you see? And then you have 3, but you no longer have any more choice beyond this part, so you have to erase this. Okay? You have to erase this. So the 3, you only have the first 3 parts, the first 3 parts of the branches. Okay? And the outcomes, of course, are as follows. If you choose 2, and then 3, and then 5, the outcomes are 3 tuples. 3 tuples. That is x1, x2, x3. Okay? It's a fraction of what we have previously. So each branch with one outcome, and this is omega 3p. What's the size of omega 3p? Omega 3p. How many fruits does these 3 have? Well, you again use the multiplication principle. Okay? You know the size, you know the multiplication principle to know how many branches you can find. And so let's call C 3p. The number of branches. Well, by the multiplication principle, you have 5, then you have 4 possible results, and then you have just 3. Okay? Very important. This number, see, because the branches are in one-to-one correspondence with outcomes, these two numbers must be the same. So, this is how many fruits that you have from U3. Okay? This is good? Now, let's now rewrite this, because it's 5 times 4 times 3, but let's rewrite this because in the long term you will see how useful it can be. First, let's complicate a little bit. Instead of 5 times 4 times 3, let's make 5 times 4 times 3 times 2 times 1. But you have to exclude this part. So we divide this by 2 times 1. Okay? You see? This part cancels, but so it is still the same number as this, but you can rewrite this using our factorial notation. This is 5 factorial divided by 2 factorial. 2 factorial is 2 times 1, or better. You see? It's 5 minus 3. 5 minus 3 factorial. Because 5 minus 3 is 2, so it's 2 factorial. Okay? So this number, okay, counts how many branches, okay, in a very short notation. Okay? Now, let's just look at it from, let's check it. Let's check it from different point of view. You already understood that you cut like this, but I'm going to give you a different point of view, because I'm claiming that 4 times 3 is equal to 5 factorial divided by 2 factorial, right? That's what I'm claiming. But rearrange it. Let's check it. Rearrange it. You have 5 times 4 times 3 times 2 factorial. You multiply by 2 factorial on both sides, equals to 5 factorial. So is this true or is this false? Well, it's true, because here is 5 times 4 times 3 times 2 times 1, this is 5 factorial. So this is indeed correct. Okay? So again, you have two ways to come up with this conclusion. You either realize that it cuts, or you just rearrange these two parts and you realize this. Okay? So you do two different strategies. We are going to use it in a minute. Okay? Now, one very important observation about this. I didn't told you previously, but I will tell you now. You see, when you make this choice, you see, you have all the 5 possibilities. But then, you only have 4. And the 4 that you have are different. You see, if you chose 2, 2 no longer appears. I already told you this part, but let's just rephrase this. You see, it's like the step number 2 is conditioned. Is conditioned on the outcomes of the previous result. You see, if the previous result is 2, you can no longer have 2. If the previous result is 4, you can no longer have 4. The step number 3 now is conditioned again on step number 2 and step number 1. So the outcomes here, the outcomes of the third step, are conditioned on what happens previous, on the history. So you can no longer have 3 or 2. You see? Very important, this idea. Okay? Now let's make this more general, because you are assuming from 1 to 5, but let's make it general. Instead of 1 to 5, let's make it from 1 to n. So we have a set of distinct elements. One, in this example, numbers, but it could be anything. It could be cards, it could be stones, it doesn't matter. Whatever distinct entities you can choose. So this is, let's call it C and P. So we choose not between 1 to 5, but between 1 to n, not between 1 to 5, but again 1 to n. This is the same, of course. You can no longer choose what you chose previously. There is conditioning. But let's make this more general. Instead of 3 steps of choice, let's make it k steps. k is an integer number. It could be 10, 100. So it again choose from 1 to n, except the step number 1, step number 2, up to the choice that you might make in k minus 1. Okay? So accept these results. Okay? Now, obviously, k must be less or equal. K must be less or equal to n. Otherwise, it makes no sense. Okay? Well, so the tree has n possibilities, then n minus 1, and then n minus 2, and so on. Okay? Let me write it. So the number of branches, let's make it general. Okay, let me just... so we have 5 times 4 times 3. I will write it downstairs for you to see. So this is the C and P, the size of this case. So while before we have 5, now we have n. While before we have 4, now we have n minus 1. And then n minus 2. Okay? Of course, because this is general, you have to keep on going. You have to keep going. You have to keep going, etc. Like n minus 3, and so on. You keep reducing. Notice, reduce by 1, and so on. And where do you stop? Where do you stop? You will stop, I'm gonna say it, and then we analyze. You stop at n minus k plus 1. That's where you stop. Okay? If you have a set with n numbers and you are making k choices, the number of realizations is this string of numbers. Okay? This string of multiplications, which ends at this weird thing. Let's look at it why it is. But before, I'm going to rephrase it. It's n factorial divided by n minus k factorial. Okay? First, how can you check that this is okay? First, you can compare. You see? You can compare. Because if n, let's write it, because if you have n is 5, and then n minus 1 is 4, and then is 3, and I mean, you just move along, and then you have 5 minus k, which is 3, gives you 3, you see? I'm gonna write it, 5 minus 3 plus 1. That's what we would do. So, but that's what? That's 3, okay? 5 minus 3 is 2, plus 1 is 3 again. So this formula works when n is equal to 5 and k is equal to 3. So it works. Okay? Let's analyze from the different point of view. So I'm going to rearrange it. Multiply both sides by n minus k. And let's see if you agree. n minus 1, n minus 2, n minus 3, and so on. You keep moving, reducing, and you have n minus k plus 1. But now we multiply n by n minus k factorial, and we claim that this is n factorial. Does this make any sense? Because it's n minus 1 and so on. You reach the number n minus k plus 1, but the next one would be n minus k plus 1, but reduced by 1. So it's just n minus k factorial. You see? So this makes sense. Okay? It makes sense that this thing is the same as this. Okay? And that's how we can check that this formula here has to end at this, and is equal to this. Okay? This is more difficult, but if you do it slowly and carefully, you can realize that this is indeed correct. Okay? So this is the general situation. Okay? And let's give a conclusion to this, because what does this number mean? Let's add it to our list of important calculations. N factorial divided by n minus k factorial. What's the conclusion? if you start with a set U with n distinct elements, it doesn't matter, it could be letters, numbers, it doesn't matter, and this number n factorial n minus k factorial means that you are taking from this set, U set, k elements, and then putting in a particular order. You see? So this the number. This is in the right. The correct name for this is you have so x1, x2 up to xk. The numbers, the elements of or the outcomes of omega np. You see, this is the elements of omega np. This is what we call k-permutations of n. You see? So you start with a set n, you take k, put it in a particular order. That sequence, that k-tuple, is called a k-permutation of n. Previously, we had something different. Remember, previously we had something different. You have the set with n elements, and you just put it in a particular order. So there is n factorial. Then you call each of these particular orders a permutation. Now the name is different. It's k-permutation of n because the size of the sequence of numbers is just k. It's not n. Okay. Now let's now move on to an extremely important concept. It's called the combinations. Very important concept, combinations. Combinations. But before I go to combinations, we will first look at this from yet another point of view. A very important one. It requires some thought. So let's call it C again, another C. This is the Kp. So let's call it this Kc because again it's Kp again because you are still keeping k permutations. So let's make something equivalent to this. Okay? I'm going to write it. You first choose a set. So first step is choose a set of k elements. So you start with a set U. You start with the U, right? From 1 up to n. And you choose a set, a subset, in fact, a subset of k elements. It could be any set. I'm going to give you an example what I mean. It could be, for example, the number 1, 2, 5, okay? If k is 3, you choose a set with size 3. Here is an example in the case of k equals 3. Okay? So you start with this U, you pick, for example, this set. Now the second step on our CKP, which I claim is equivalent to this, is the following. Is choose a permutation for the set. Okay? What does it mean to choose a permutation? Because in a set the order doesn't matter. You could have chosen equally 2, 1 and 5. It's the same set. Okay? So when I claim that I choose a set with k elements, I mean choosing distinct sets. So it's not if you say, okay, I chose 2, 1, 5. Well, that's not a distinct set. It's the same as this. But now on the step number 2, you're going to choose a permutation. So I'm going to choose an order for this. For example, 5, 2, and 1 is a particular permutation. Okay? So you come here and this. There are other possibilities, but now you can see that following this just two-step recipe is producing the same as this. Okay? In the case, of course, in the case when n is equal to 5 and k is equal to 3. Okay? Can you see? Because this is equivalent. These two procedures are in fact equivalent. Equivalent. These two things are equivalent. However, you know the multiplication principle, and you have here two choices. So that means the following. It means that the size of Kp here must be how many ways you can realize this thing, how many choices of K sets you can make. This is a very important number, but we don't know it yet. Okay, you don't know how many ways you can realize this, because it's like because you don't know it. Let's make it an unknown. Let's give it a name and a variable. It's a variable. So let's call it this weird symbol n and k. Okay, this weird symbol is a number that represents how many ways you can choose subsets with size k out of a set with n elements, distinct ones. So it's this number, how many ways you can realize step 1, times how many ways you can realize step 2. Well, step 2, you have a set with k elements. You see? Because you are choosing a permutation for the subset with k. But you already know, if you start with a set with n elements, then the number of permutations is n factorial. Here the set has k elements, so the number of ways in which you can choose permutations is k factorial. So it's k factorial here, okay? But I told you, you can actually see this, because following this recipe is the same as following this recipe. But you know how many ways you can realize this recipe. How many ways? CKP, how many ways can you realize? Well, it's written here. It's again n factorial n minus k factorial. But now you can start to see, because you have here the unknown, the only unknown in this equation, so you can figure out what this unknown is. So this implies that n, this number, this strange number, is in fact, you just rearrange, you see? You just divide by k factorial on both sides, and you have n factorial divided by n minus k factorial divided by k factorial. Okay? Very important result, because now you know. Now you know how many ways you can choose subsets with k elements from a set with n. That's what this number computes. Let's add it to our wonderful list of calculations. So now you have n factorial. Let's put a little bit lower. N factorial. It's almost the same. N minus k factorial and k factorial. And that's it. Our last result today. How many subsets can you make with this? Okay. Now that you arrive at this point, you already seen the most important ways in which you can use your multiplication principle. Remember, comes from the multiplication principle, applied to different situations. We are going now to the final stage, in which we are going. It's a bit difficult. It's a bit difficult, but it's very illuminating once you see it. We are going to look at the interpretation of these ratios. You see, let's see why these ratios work in this final part of the lecture. So let's see if you can survive this part. We are going step by step again. I really hope you can see now this part. Let's see. We will start with an example. We will start like this. Let's start with n factorial. Remember, what's 5 factorial? You have a set with 5 distinct elements, and you have 5 factorial. That tells you, see, let's consider the set from 1 to 5. It's easier. So you have the set with, for example, it could be 1, 2, 3, 4, and 5. And 5 factorial will tell you how many permutations can you make from this thing. Let's give an example. From 1 to 5, you could have 1, 2, 3, 5, 4. Or you could have 2, 1, you just flip this, 3, 4, 5, or 2, 1, 3, 5, 4. Let's give one more example. Let's now switch these two things. 1, 2, no, I'm sorry, these two. 3, 2, 4, 5, or 1, 3, 2, 5, 4. Can you see? Let's choose another one. You could have the thing in reverse. 1, 4, 3, 2, 5, 4, 3, 2, 1, or 5, 4, 3, 1, 2. You just switch the last one. Or let's just exchange the first one, 4, 5, 3, 2, 1, okay? Or 4, 5, 3, 1, 2. Or finally, let's exchange now these two, and you have 4, 3, 5, 3, 4, 2, 1, or 5, 3, 4, 1, 2. Just exchange the last one. You can keep on going with this. Okay? Now let's analyze the thing that our work. Let's analyze this. Because is the idea. And 5 factorial tells you how many entries on this table. How many entries you can find on this table. Can you see? Because on this table you will find all the possible permutations of a set with 5 elements. Okay? More. Let's now organize. I organize this thing in a special way. So the organization is as follows. I split the number of 5 into parts. The first 3 numbers, I call it the heads, and the last 2 the tails. So you can find heads and tails, heads and tails, heads and tails, and so on. And here the same thing, heads and tails, heads and tails. So once you see the pattern, let's see. On this particular box, the heads switch. On this particular box, the tails switch. The heads remains the same, remains the same, remains the same, switch. And I keep on going with this, okay? Now, what's the size? What's the size? So the size of the heads is 3. The size of the tails is 2. Okay? In general, the size of the heads is not 3, but it's what? It's k. The size of the tails is n minus k. You can see that k plus n minus k is n. N is the size of this string of numbers. Okay? What's the size of the box? The size of the box, let's use it. How many elements can you find on the box? Well, there are in this box as many elements as there is permutations in the tiles, right? But how many permutations can you make with the tiles? Well, we use again, it's k factorial, n minus k factorial. That is 2 factorial. So this is 2 factorial, or in general, n minus k factorial. You see? Very important results. But now is the crucial observation. The crucial observation is this. Let's draw here another set. Each one of these boxes, 1, 2, 3, is in 1-to-1 correspondence with these 3 tuples. You see? This is the heads part I'm writing here. 5, 4, 3, 4, 5, 3 here. And finally 5, 3, 4. See? I'm going to write it like this. So if you have each one of these boxes, this box or this box of size n minus k, and so on, this corresponds to this one corresponds to this one, and this one corresponds, and so on. You see? There is a one-to-one correspondence between the boxes in this table, which has n factorial entries, and the number of elements in this set. This set, if you remember, is what we call omega previously, omega 3p. Now, how many boxes do you have here? You see, if each box has size 2 factorial, and there are 5 factorial entries in the table, then the number of entries here must be n factorial, or 5 factorial, divided by 2 factorial. You see? Or in other words, 5 minus 3 factorial. Or is 5 factorial? 5 minus 3 factorial. Okay? Or in general, if you just have a sequence with k, with n elements, I mean a set with strings with n, and the heads measures k, then how many entries did you find on this table, how many boxes do you find on this table, is n factorial divided n minus k factorial. You see? But because each box here is in one-to-one correspondence with these 3 tuples, then that means that this number, the number of boxes, is the same as the number of 3 tuples in this set. Okay? Very important observation. You see? And that justifies this formula. You see? The numerator is telling the size of the table, and the denominator is telling the size of the boxes. And so the ratio means how many boxes can you find. But because the boxes are in one-to-one correspondence with the heads part, or the 3 tuples, well, there is these 3 tuples, as many of these as there are boxes. Okay? So these numbers, if you recall, are what we called 3 permutations of 5. So this is called 3 permutations of 5. Okay? These elements. Let's now look at the final one, the more difficult one. You see? We already understood part of it, but there is this mysterious k factorial. Let's look at it. You see? Let's analyze. Look at this part. This column. This keeps on going. These columns. What's happening in this column? So you have 1, 2, 3, and then different orders. You see? 5, 4, 3, and then different orders. So in this column you will find all the orders, all the sequences that you can make, all the permutations. Okay? The same here, the heads part on this column, you can find on the heads part here the same, here the same, but they are different sequences. Here the same thing. If 5, 4, 3, 4, 5, 3, and 5, 3, 4. So this is different sequences. The heads has different sequences. So the question now is, how many boxes can you find? How many boxes can you find on this column? On this column, I'm sorry, like this, because this keeps on going, or this column. How many boxes do you find here? You see? This is very important, because you can see, let's look at it. Because you are switching elements, here, switching, you keep on moving, then that means that there are in this column as many boxes as there are permutations of the heads. Can you see? There are as many boxes as permutations, but how many permutations can you make on the heads? So the size from here to here, this length, how many boxes can you find, is the number of permutations of the heads. But this is k, or 3 factorial. So there is 3 factorial permutations. Or, in other words, k factorial. You see? Now, if you divide now the number of boxes, which is given by this number, by the size of each column, which is k factorial, you get the number of columns. Very important idea. Can you see? If you divide all the boxes by how many boxes there are in a column, you get the number of columns. And that's exactly what this number is giving you, the number of columns. So this is the first column, this is the second, it keeps on going, up to n factorial, k factorial, n minus k factorial. The last column that you would find. Okay? Very important idea. We already computed the number of columns. But here's the final revelation, let's say. Because there is another set. There is another set here. What's this set? Can you see? This set, see, for each column, you have all the permutations of 1 to 3. For this column, you have permutations of 5 for 3. So, it's all the permutations of the set of 1, 2, 3. Here you find all the permutations of the set 3, 4, 5, and so on. So there is a one-to-one correspondence between this column and this set, or this column and this set, or whatever column you can find, and another set. Because you start with this set, you make all the permutations, you get the column. You start with this set, make all the permutations, you get this column. So there is a one-to-one correspondence. But this is a major consequence, because you know how many columns there are. You see? It's this number. So the number of columns is actually counting how many sets you find here. Okay? And these are the subsets of our original U with 5 elements. And this is why, from this more abstract point of view, why this ratio has to give you the number of subsets with 3 elements, starting with a set with 5. Okay, this is all for today. You can find, you actually have to stop and think about these things. Do the exercises, make pictures if you want. You can find in the description the notes and also the exercises. I wish you a good work and see you next time. Goodbye.